In this video, we're performing truss analysis using the method of sections. So for this example, we're going to calculate the forces in members CD, CI, and IJ. So in my previous video performing truss analysis using the method of joints, it took a long time to work through this truss, performing calculations at every joint along the truss structure. So if we want to find the internal forces in members CD, CI, and IJ, as they are towards the centre of the truss, it would take quite a long time using the method of joints to get to these members. So instead, we can use the method of sections, which will be faster. So taking one of the triangles, assuming that all 7 triangles are the same, we have a perpendicular height of 1.5 meters and a width of 1.73 meters. If I bisect this vertically, drawing a dotted line, I can create this into 2 right-angled triangles. So now for the right-angled triangle, the height is 1.5 meters and the width is 0.86 meters. So using trigonometry, I get that the angle theta is equal to inverse tan of the opposite, which is 1.5, over the adjacent, which is 0.86, which gives me an angle of 60 degrees. So by the symmetry, the angle on the right-hand side also has to be 60 degrees, and this means that the angle at the top in the original triangle is also 60 degrees. So each of these triangles in the truss is an equilateral triangle with 60-degree angles. So the first step is to calculate the support reactions for the truss. So if we identify the reaction types at each of those supports, so support A is a pin joint, so it allows rotation, but it restricts movement in both the X and the Y directions, so this gives me support reactions AX and AY. Support G is a roller, so this allows rotation, it allows movement in the X direction, and it only restricts movement in the Y direction. Therefore, I get a support reaction GY. So to find the values for AX, AY, and GY, I can use my 3 equilibrium equations. So the sum of the forces in the X direction is equal to 0, the sum of the forces in the Y direction equals 0, and the sum of the moments is equal to 0. So I'm going to start by taking the sum of the forces in the X direction, as I only have one of the unknowns which is in the X direction. So for the X direction, anything going to the right I take as positive, and anything to the left is negative. So the only force that I have going to the right is AX. So I get the equation AX is equal to 0. So I can remove that arrow from my diagram. Next, I'm going to take moments. So taking moments at A will eliminate the AY from the equation, because moments is force multiplied by perpendicular distance. And the distance of AY from A is 0, so that AY is multiplied by 0, which eliminates it from the equation. So for moments, I take anything going counterclockwise as positive and clockwise as negative. Fixing the point A, for working along the truss, the force of 10 kilonewtons acts down on top of the truss, so if A is fixed, this would turn it in a clockwise direction, which is negative. So the moments for this is minus 10 multiplied by 0.86, as the 10 kilonewtons is 0.86 meters horizontal distance from A. Next, I add on the 15 kilonewtons. So again, this would turn the truss in a clockwise direction if A is fixed. So it gives me negative moments. So I have minus 15 multiplied by 4.31, because this is 2.5 of those equilateral triangles. So it's 4.31 meters away from A in a horizontal direction. And then the final force, I have GY. And this is 6.9 meters away, and this one would turn the truss in a counterclockwise direction as it's pushing up from underneath. So this one is going to give me positive moments. So it's plus GY times 6.9. And all of these add up to 0. So I can rearrange. This gives me that GY is 10.63 kilonewtons. and I can add this onto my diagram. And my final equation, the sum of the forces in the y direction is equal to 0. For this one, taking the upward direction as positive and downward direction as negative, the forces going upwards is the AY, so it's plus AY. So also going up, I have the GY, which is plus 10.63 kilonewtons. And for the downward direction, I have minus 10, and I have minus 15, and all of these add up to 0. So rearranging and simplifying, I get that AY is 14.37 kilonewtons, and I can add this onto my diagram. So for the method of sections, I'm now ready to make my cut. So I'm going to make my cut all the way through the truss, through those three members, CD, CI, and IJ. I'm imagining I'm slicing through the structure into two separate parts. So I'm isolating the left side of the truss. And I replace the cut members with forces acting at the cut. So when we make the cut, we assume that all of the internal members are under tension. So even though the truss is intact, really, what I'm doing is I'm exposing the internal forces in those members and turning these internal forces into external forces on my chosen section. So instead of analysing the whole structure, I'm saying, if I pretend this part is separate, what forces must exist at the cut to keep it in equilibrium? And then I apply my equilibrium equations. So I'm going to start by taking moments at C. So again, taking moments at a joint will eliminate those forces from the equation. So this is going to remove the two unknowns FCD and FCI, leaving me with one unknown Fij. So again, taking moments in the counterclockwise direction as positive and the clockwise direction as negative, fixing C. If I apply the 10 kilonewton force at joint B, this would turn the truss in a counterclockwise direction. So this generates positive moments. So this gives me 10 times 1.73, as the 10 kilonewtons is 1.73 meters from C in the horizontal direction. Next, taking the 14.37, if C is fixed, this force would turn the truss in a clockwise direction, which gives me negative moments. So I take minus 14.37 times 2.59, as this force is 1.5 of those equilateral triangles away from C in the horizontal direction. And then the final force I have left is the Fij. So if C is fixed, this would turn the truss in a counterclockwise direction, so it gives me positive moments. So I do Fij multiplied by the 1.5. So note that the Fij is a horizontal force, so I need to take the vertical distance, and the Fij is 1.5, which is the height of that equilateral triangle. So it's 1.5 meters away from C in the vertical direction. And all of these add up to 0. So rearranging and solving, I get that Fij is 13.29 kilonewtons. Next, taking the sum of the forces in the y direction. So taking up as positive, down as negative. In the upward direction, I have 14.37. And then downwards, I have minus 10. And I also have minus FCI sine 60. So this is the vertical component of FCI if we resolve it in the vertical direction. So these add up to 0. Then rearranging and solving, I get that FCI is 5.05 kilonewtons. And I can add this onto my diagram. And finally, taking the last equilibrium equation, the sum of the forces in the x direction equals 0. It's taking anything to the right as positive, anything to the left as negative. I have, in the positive direction, FCD. I also have 13.29 kilonewtons from Fij. So I also have the horizontal component of FCI, which is 5.05 cos 60. And all of these add up to 0. Rearranging and solving, I get that FCD is minus 15.82 kilonewtons. Therefore, this member is under compression. So when I add it to the diagram, I turn the arrow the opposite way because that's what the minus sign means. It means it's 15.82 kilonewtons, but in the opposite direction. So we found all of the forces in the members CD, CI, and IJ.